What's up, everyone? I hope everyone's perfect, listening to good music, finding good playlists, watching good sport, and doing fine. This is Divyanshu, and I welcome you all again to this playlist on oil and gas data analysis and machine learning with Python. So, in the first two videos, we have discovered how we can connect with Python as a petroleum engineer. Like we discussed about Newton-Raphson's method, we discussed about the application of Newton-Raphson's method on a typical reservoir engineering problem, which is known as Klinkenberg effect problem. So we learned how to, solve a simple challenge and try to simulate a laboratory problem using Python, right? So this is something which is very good. You feel more confident about applying petroleum engineering concepts as you keep on learning more and more Python tools, because the difference that I felt when I was learning Python and when I was not knowing Python was that when I was not knowing Python, I would read a concept, I would understand it, and I would be happy about it. But there would be still this incomplete feeling where I still had not applied it. But now with Python, you can apply this concept to, you can see graphs of a function that you read long time back. You can see Darcy's law in action. You can make a widget out of it. You can do various things that gives you instant gratification. You feel satisfied, right? So today is something similar that we are going to do. We are going to do a mini project which will give you a heads up and which will give you an idea what a typical data analysis project looks like and what tools are used. We are going to look at a few tools today, just a sneak peek or something like that. We will be going on to the details of these tools later on, but we will be looking at tools like Matplotlib, which is a plotting library in Python. And we will be doing a very interesting and one of my favorite problems, which is known as nodal analysis. Let's talk a bit about nodal analysis, guys. What do you understand by nodal analysis? It's something for non-petroleum engineer guys. It's more like everyone's read Kirchhoff's laws, right? So it's from current electricity or circuit measurements. What happens when current flows from various circuits are drawn, right? If you remember Wheatstone Bridge and things like that. So to find out the measure of current that flows from a particular node to the distributions from there on, we used to apply various equations, right? So whatever is coming onto the node is equal to whatever goes out of the node. It's more like a law of conservation of something, something that comes in. I won't say energy because currently we are talking about electricity, or it can be applied to a lot of cases. So let's not make it particular. So whatever comes in goes out. In oil and gas, of course, it's more law of conservation of energy. What nodal analysis says is that if something is coming in, that exactly is what goes out. In pressure terms, we can talk about this. In pressure terms, we can continue this concept. Think about the journey of oil. The oil is lying at, somewhere far away in the reservoir rock pores at an initial pressure PE. Okay, it starts its journey from there. The reservoir deliverability, or the power of the reservoir to deliver oil from itself, from its own stomach to the wellbore, is called the IPR. We want to try and find out what's the reservoir capacity to deliver oil. And the measure of the capacity or the power of a reservoir is measured, in my language I would say, you put a pressure gauge at the foothills of your well, which is known as a sand face. You measure the PWF, which is the flowing bottom hole pressure. The higher the PWF, the easier the oil found it while it was flowing from the reservoir towards the wellbore. So that's a good IPR, right? That's a good inflow performance because the oil did not lose much of its energy when it was coming from the reservoir up to the wellbore, right? But there are cases where there is a huge formation damage, there's a skin factor, things like that, which take away all the energy of the oil, which is also quantified using the Hawkins concept, where we find out the dimensionless skin factor and things like that. We can find out the delta P skin and things like that. So that is that what that does to the oil is it reduces, it depletes its energy as it comes towards the wellbore. You know, most people think of it in different ways, but this is a very nice visualization. Imagine you are sitting on top of oil droplet which is starting its journey from the reservoir and trying to flow towards the wellbore, you will experience that down the lane, as it flows from the reservoir to the wellbore, it loses its energy as it flows through the porous media, right? So this is exactly what IPR is. Once the reservoir has delivered oil to the foothills of the well, which is known as the bottom hole, taking oil from there on up to the surface is something which is known as the tubing performance relationship or the vertical lift performance, right? And if we draw curves of inflow performance and outflow performance, the concept of nodal analysis says that at that particular node, the pressure must be 1, not the magnitude 1, but the pressure must be unique. There cannot be two pressures at the bottom hole. There can only be one pressure. So if you call the external reservoir pressure as PE or P bar or anything, and the bottom hole pressure as PWF, then P bar minus PWF is more like the quantification of IPR, and then PWF minus the P wellhead is more like the quantification or the differential for the vertical lift performance. But focus on this single point, that we are just taking the common PWF for both sides of the story. We are not taking for inflow performance one value of PWF and for outflow performance another value of PWF. So that's the important concept. In other words, this is exactly what nodal analysis is. If you think about it in graphical terms, if I draw the curve of the IPR, and if I again draw on the same plane the curve of the TPR or the VLP, they will intersect at a particular point, and that exact point is called the node. That is the pressure of the node, and the flow rate corresponds to the operating flow rate of that node, right? So that is, now talking about nodes, there can be various nodes in the reservoir, in the production system. Most common node is the bottom hole. Most people take the wellhead as the node, but the entire concept is simple. You just have to follow the journey of oil. It starts from somewhere, it ends up to the separator. It starts from the reservoir, it ends up to the separator. So just keep on writing the pressure terms one by one up as you go along the journey of oil. So if I had to write my equation for this pressure profile, I would write it something like this. I should write it in front of you guys. So this is, I hope it's visible. So P external or P bar is my reservoir pressure. So this is my reservoir pressure. Then as oil flows from the reservoir to the wellbore, let's say delta P reservoir is the pressure loss in the reservoir. So I'll call it delta P reservoir. So this is the delta P reservoir. This gives you what? PE minus delta P reservoir gives you PWF. So this is the first equation of, what do you call it? The first equation. Okay. So let's say this is the PWF IPR. Okay. And for those who don't want to, just those who already know about, IPR and TPR, they can just skip on to the later section of this video where I talk about basic Python code. But currently I'm talking for those who are new to this concept. So PE minus delta P of the reservoir gives you the PWF IPR as we have traveled from the external point of the reservoir towards the wellbore. Then this is IPR, okay? This is the equation for IPR pressure differentials. Then we start from PWF of PWF of TPR. Let's say we are not following the nodal concept right now. We are assuming there are two different pressures at the bottom hole, okay? And then I will conclude what I mean by the nodal analysis. PWF at TPR minus of delta P in the tubing. Let's assume we are producing through a tubing and not a casing, which is very rare, by the way. We always produce by tubing or something. That gives you the PW minus, okay, let's call it minus PW del P of surface lines, gives you the pressure of the separator. What I'm saying is the entire system is the reservoir rock, then the bottom hole, then the tubing, then the surface flow lines, and then comes the separator. This is the entire journey of oil. So if I just keep on shifting things around, this thing comes to the right hand side. So I can just take this thing, Control C, Control V. Oh, I could have done Control X. So this comes right inside. And this equation is for the TPR. Okay? And this equation is for the TPR. And according to the nodal analysis, PWF at the TPR should be equal to PWF at the IPR, because at a particular node there cannot be two different pressures. They have to be one pressure. So the ultimate concept becomes PE minus del P of R equals this thing, because we are equating the two equations. And this is the final. So basically what we have done, so assume this is one function which is known as IPR, and this is another function which is known as TPR. And once we draw the curves of first function and the second function on the same plane, there will be an intersection, which is the PWF value. That's how we solve two equations to find out the common root, right? The intersection of the roots. So let's go forward and talk about Python now, my favorite part. So let me just pause and reconnect to the yeah, so we are connected to the runtime. By the way, I'm using Google Colab for this, so if in case anyone had a doubt. Okay, so there are various tools for data analysis. Basically, the most three powerful tools are NumPy. NumPy is more like the computation tool for yourself. I call it the Casio 991 MS, the calculator of Python. You can do various calculations using NumPy. The most common application or the most common product of NumPy is a NumPy array, which I will tell you in my later videos. I will cover them one by one. Today is just a highlight. Then today, most common application will be of Matplotlib. Okay, it's called the MATLAB plotting library. Its Python version is called matplotlib.pyplot, and we are imploding because we cannot just keep on writing this long name. It's just like Divyanshu. It's a very long name, so we call it like an alias. We call it PLT, right? This currently you don't need to do this. It's matplotlib inline. It's called a magic command. What it does is it displays the plots right below the code cell. Okay, so for those who don't understand this, you can ignore it. Okay, so NumPy, we are not using it. So just a slight introduction. If you want to command anything and prevent it from executing, you just have to put a hashtag in front of it. Okay, so if I remove the hashtag, you can see it comes back into action. So if I don't want to use NumPy today, so I'm putting it into commands. Okay, so this is the first cell that I run. I press shift plus enter. Let's move forward, and yeah, so this is a common data set that I have gathered from PetroWiki. All due respect, so I have taken this data from PetroWiki. So uh, so IPR is basically plotted between flow rates and PWF. So for various flow rates, we plot PWF on the y-axis. So it looks like a curve, and we can see how it looks like. So basically, for basic syntax of plotting using Matplotlib is, since we are calling it as a name PLT, so we just do PLT dot plot, and whatever we want at the x-axis and whatever we want at the y-axis. So this is the basic syntax. We can do more customizations, but this is the basic syntax right now. Okay, so as you can see, we have mentioned these data points in list. Okay, so you can take the column from an Excel sheet, put it into a list. Later down the lane, the best practice is to put it into a NumPy array. Okay, more like for those who know C++, it's the exact same kind of array. Okay, it's a one-dimensional vector or something like that. But currently we are going through list because it is a very simple project we are doing. So flow rate points are mentioned like this, and the PWF points are also mentioned like this. Okay, then what we do is we create a dictionary. Okay, this is just a practice. So we create a dictionary whose key is PWF, and this is it, and whose Q is this, and we are putting exactly this data, Q data here, and PWF IPR data here. Okay, or we could have done what we could have done is, we, rather than writing it again and again, we could have just provided PWF IPR, and this is what QIPR, right? So this is Q underscore IPR. All right, so we have put it into a dictionary. Down the lane, when we understand pandas, I will teach you how to put this dictionary, go one step ahead and create a table of it. I can show you right now also, just for the sake of it, but let me just first run this so that we see there's no error. So we have a dictionary now. Okay, whatever data I have in PWF, it's stored here, and for flow rates, it's stored here. Now I just want to show you how a data frame looks like. So I just want to decomment it, control hash. So let's call it data frame. All right, So let's see how a data frame or a Python table looks like. IPR, DF. All I have done basically is put this thing, this entire dictionary inside this pd.data frame command. Okay. And bam. So we have a table now. Okay. You can see the column headers, PWF and Q, and they are displayed. So this is a simple introduction. Now this is, by now we have created the IPR dataset. Now we can just plot it out. Okay. So PLT dot, so x-axis, what is x-axis for IPR? It is flow rate, right? QIPR. And what is y-axis for IPR? Y-axis for IPR is PWF IPR. Okay. And like I told you, to plot in Python, we do PLT dot plot x IPR, comma y IPR. Here we go. Tell me it does not look like. Tell me. It does look like what we have read in the books. Brilliant. So we are now applying what we have read. We are creating from data. Who would have thought? We cannot just blindly trust. Okay, we see this data in a book, and we trust that it might look something like an IPR curve. But what about checking it for yourself? This is what we do in Python. We check this by ourselves. Okay, so this style might look different in your computers. It might like look different in your friend's computer. I have chosen a style which is known as 538, so don't worry about that. Now if I want to add a x-axis label, plt.x label, this is the command which adds an x-axis label. Okay, so x-axis label is pwf in psi. I run it again. Oh shit, I created a error. So this is basically flow rate, right? Q of oil in barrels per day. This is my X label. You can see it comes up. Similarly for Y label, plt dot Y label pwf psi. Okay. And similarly for title, you can also add a title, plt dot title. What is the title over here? IPR curve. And you can see the title also comes up. What if we want to change the figure size? So we can do it something like this. This you don't need to remember this, guys. This will get better and better as we go on practicing. plt.figure. Colab also provides a guideline. As you keep on typing commands, it provides suggestions what can be typed next. So fig size equals to, let's say I want 8 comma 4. So 8 is the horizontal length and 4 is the vertical height. Okay, so let's see how it looks like. Nice, it looks really nice now. Okay, so this is my IPR curve. Next up we will be doing TPR, and then we will be plotting both of these things in a common plot and see how we go ahead. Okay, now one thing you must have noticed is the larger the tube, the larger the production tube, the larger will be the operation flow rate. Okay, because more and more the tube size, more and more oil can be carried out. So this is exactly what we will find out using this analysis. I have data sets for 3 tubing diameters, the TPR data sets for 3 tubing diameters. I will plot them, all of them, in one by one, and basically we will find out the best TPR looking at what TPR provides us the best flow rate. Okay, so this is the flow rates. This is more like the common flow rates that I have taken in the first case. Now this is P underscore 190 is basically it's the TPR pressures for 1.90 inch production tubing. Then this is TPR for 2.375 inch tubing, and this is for 2.875 inch tubing. We know the concept that larger the tubing size, the curve should intersect the more and more towards the right. But we cannot believe it because just we have read it. We have to apply it to believe it. That's what we will follow from these A's, right? So let's do this exact thing which we have done for the IPR. Let's do this exact thing for a TPR. First, create the lists of all of these guys, then store them all in a TPR dictionary, which is more like a storage container. You can also store it in a data frame, which we are not doing today because we are not looking at pandas. I just provide shift plus enter. Just for notes, I'm putting it. Plotting in Python is done using Matplotlib. Another option like Seaborn, it's a very nice library, statistical plotting library. which we'll be using in machine learning projects later down the lane. So this is the plotting case. I will explain it what each and every term means. Already you know of a bit of these things, but you can play around with these guys. This is a very customized plot. I will plot it, and you can see the TPR for 2.875 inch intersects towards the rightmost point. And that's the concept we have just thought about, and now we have applied it in Python and we have finalized our conclusion. Okay, so that concludes a project, but let's understand how we plotted every curve and how we did what we are looking at. So plt.figure you guys already know. Okay, this style is 538. Let's try a different style. Let's try default. All looks like this. It can be, it depends on you what you want to prefer. Let's say we want to do seaborn kind of plotting customization, and it looks like this. Okay, let's keep it this way. It looks more neat to me. Okay, now plt.plot IPRQ. So IPRQ, and it's like calling the Q flow rate from the IPR and the pressures from the IPR dictionary. So you remember from the Python playlist, you remember that you can call the values of a dictionary by mentioning the keys inside the square brackets, right? So Q is the key of the dictionary, and PWF is also the key of the dictionary, and it brings out the exact values of the dictionary. Okay, line width you can provide as a parameter. Line width is 1.5 over here. You can provide a label as well. So you can see this label is coming over here. So ultimately we'll be providing a plt.legend. This is a legend we are going, but for a legend to appear, we have to provide, for every plot we have to provide a label parameter, right? So so we have provided label for IPR. Similarly, we are doing a plot individually for all the tubing sizes. We are providing label as well. So for those who are not clear, basically we are calling this value, this list, using TPR square brackets Q. Similarly for this, if you want to call this, we do TPR square brackets this thing. So dictionary name square bracket key name gives you the value. And what is the value over here? The values are all the lists over here, right? If you want to refer back to the dictionary playlist, you can go back to our Python for oil and gas playlist from Petroleum from scratch. I will provide it over at the top over here as a suggestion, and you can refer and come back to this, right? So we are plotting one for 1.90 inch tubing, then for 2.375 inch tubing, then for 2.875 inch tubing. Just so we have clarity which one stands for which, we are also providing the label for each of these guys, and then we are providing X label like we did, then we are providing Y label like we did, we are providing nodal analysis as the title now, and then finally we are doing plt.grid, and finally we are just plotting it, right? So that's how we do it, and this completes your first basic and a very interesting nodal analysis project in oil and gas. So you can call it a reservoir engineering project, you can call it a production engineering topic, and it feels good when you see plots that are there in your mind. You can see on Python as well. So with that note, on a great confidence level, uh, see you guys, and we will see you in the next video, where I will share more and more important topics, and we will keep on going with this playlist. Very excited. See you again. Cheers.